Hello everyone, today I'm going to show you how to assign material properties in hypermesh. So here we have a model that we have meshed before, so everything is here. Before we assign material properties, the first thing we need to do is to move the bonds from each other, because now you can see these two cartilage areas are penetrating with each other. If we use their current positions, it will definitely lead to errors when we run it in Abaqus. So first thing we need to do is to leave enough gap between any contact. Okay, so first I'm going to move these two pieces of bones. So we use translate, and then we click these two elements and select attached. Now you can see we have selected these two pieces of bones, and then we define a distance here, and we are going to use their axis because we want to move it away from talus bone. So we are going to click translate plus, and you will see these two pieces of bones will move up. Yeah. So once you are done, you can click return. Okay. Now you can check if tibia, fibia, cartilage, and tibia cartilage are still penetrating each other or not. You can see here, from here to here it's good, but for here you can see there are still some penetration. So we need to move this a little bit away along this direction. Okay, let's display all meshed elements. Okay, click this one, this one. Okay, so we are going to move the tibia bone along the x-axis. So in order to, you need to write down these numbers. So first we move the tibia and the fibia +3. Okay, we are going to need this displacement to bring it back when we import the model in Abaqus. That's why we need to write it down. Okay, so next step, I'm going to move this piece of bone along the x-axis. We don't need it that far, maybe 2.5. And we click OK, and then click return. Now you can check tibia. You can see here we don't have any contact here, and here it looks all good. See, there is no penetration anymore. So we check. Yeah, we use the 2.5 along the x-axis. Actually, it's positive x. Yeah, positive x. Okay, so you need to put x-axis 2.5 and put here 0 because we didn't move along y-axis. Okay, now tibia is done. Let's try to move fibula. So tibia is down. You can see fibula. You can see there are some penetration here, and not very much. So you need to show off there, and maybe just move 1.5, and still along x-axis, but it not this time is selective. We want to move fibula along this direction. So you click here. Okay, you have to select it first. Now we can check. Now it's good. Click return. So it's 1.5, but it's selected. 1.5, and here is 0. Okay. Let's go back. So now these two pieces of bones are done. Let's move calcaneus bone. So go to translate, click this one, and attached. Let's move this piece of bone along that direction first. So let's give this 3.5 and tap. You can see here we still have some penetration. So what you can do here, we already move lactic 3.5. So here, because we don't have much room along other directions, so I'm going to continue move this piece of bone along that direction. This time I'm going to give just one. Okay, and so just in case you put here, let's do 1, so it's 0.5, right? Let's check with calcaneus. So you can see here we still have some penetration, but we can move the entire piece of bone along this direction because we have some room here. So we are going to move this along this direction of calcaneus along y direction. So select the y direction. Okay, let's give 0.5 and see 0.5. We can continue doing that. 0.5. So we clicked it twice, right? So it will be 1. So along y direction, it will be 1. Right? along this direction, y direction, it will be 1. So we will put z x0. Now if we click return, double check. You can see here we have some distance between these two cartilages. Okay, now calcaneus is done. So we are going to move the last piece of bone, which is lavicular. So let's select lavicular first, and let's move along that direction first. So I'm going to give a very big displacement because their penetration is relatively large. So I click translate methods. Okay, let's go back just in case. Okay. So select this one along that direction. Click. Okay. So it's that direction. It's lactic 3.5. Now we are going to move it along y direction. So it's still lactic. Maybe we give a small, maybe 2. So put 2, and this one put in there. Let's check if we need a further translation or not. So lavicular. So you can see the surrounding area is all good. Just in case, if you wanted to check the bottom part, because it's not visually convenient, so you can select mask and select this part, hold shift and select this part and use mask. You can see, yeah, it looks good. And after you are done, you can see, you can select unmask all. Okay. So now you can see all pieces of bones were detached from each other. So this is what we need. Okay, because if there is any penetration between any two pieces of bones, you will have error in finite element model. So this part is the displacement that we needed to move surrounding bones from talus. And later we are going to bring them back in Abaqus. So here you need to change the sign of this displacement in order to bring them back in Abaqus. So you can see I changed the sign of each number. It means I will bring these pieces, bring all surrounding bones back in Abaqus. You can just remember this number. Yeah, I'm going to use these numbers when we set up Abaqus. Okay, next part we are going to assign material properties. So you can see here we have two two components. I mean two kinds of materials. We are going to use one material for bone, another material for cartilage. Okay, let's create a material. Let's click material, create, and you can give a name. I would like to name it, I would call the first one cortical bone. Cortical bone. Okay, and then you can see it's a linear elastic. You can choose the elastic, and here you give two parameters. The first one is 19,000. The other one is 0.3, and then you click close. Now you have created one material called cortical bone. And next we are going to create another material. We call it cartilage. Cartilage. So, but for cartilage, we are going to use the hyperelastic model. So we are going to choose the material model called Ogden, and we need to define three parameters for this material. The first one is 2.43. Second one is 12.45. The last one is 0.176. Now this material, okay, sorry, it's done. Close. So this is the biological model. We don't have any implant here, so we don't need this material property. But if you are going to change talus bone to other implants, like customized or SSM later, you need to define another material for that implant as well. Okay, for this model, you just need these two kinds of material properties. And next part, you need to create a property. You need to create properties, and here you need to give a name. For example, I'm going to call it cortical bone. It can be seen, okay? And for the material, you just select the material you have created earlier. And here, you should use a shell element, shell section. And if you are going to use shell section, you need to define the thickness. We are going to use 0.1. Okay, and click close. Now you have one property for all these bones, and then we are going to create another properties for cartilage. And here we need to use a different section. We are going to use solid section here. Okay, and for solid section you don't need to define thickness, and you click you select cartilage material, and that's it for cartilage. Okay, and now we have two properties. Now we need to assign these two properties for different components. So I can show you these parts all cartilage. And for this part, these for these parts, for these bones that you can see here, we are going to assign cortical bone material properties for them, and for the rest, we are going to assign cartilage. If you can select all of them and click assign and give material properties, cortical bone, and click OK. If you after you successfully assign the material property, you can see if you click them, you can see here you have material property. But for this one, you can't see. It shows undefined, unspecified. Okay, you can do it one by one if you want. We're going to put cartilage for this one. Okay, and you can also select all of them and right click and assign cartilage. Click OK. Now you can see all them have correct material property. So if you are not sure if your material properties have been assigned to all pieces of bones, you can click here, materials view. Okay, you can see all green color shows that shows those bones that have cortical bone material properties, and the blue color shows those components that have cartilage material property. Okay, now you have all now you have assigned all material properties you need, and your model is prepared. Next step, you need to export this model so that you can put it in Abaqus and run it. So in order to export this model, you click export here and click solver dick. And you can give this model a name. For example, here it's not talus flexion, it's planned flexion. So I'm going to put it here and call it PF-bio, because this is a biological model. And you click C. Make sure you click custom and now you need to make sure that here file type should be Abaqus and the template should be standard 3D. It's default options, but sometimes you might need to double check it. Okay, now you click export. Once you can see finish the scan here, it means your model has been exported successfully. You can find it under this folder. So here is your model. You can see you have just created this one, and when you click, you can see it's very beautiful. Everything is here, and but here at the very beginning of at the very end of this file, there are some redundant information here. You can just select all of them and click delete. That's it. Otherwise, if you import this file into Abaqus, you would get some volumes. Okay, it's not visually appearance. That's why I like to delete all of them. And click save. And now you can just close and close this software. Next, I'm going to show you how to use Abaqus. You need to open Abaqus C. Now you need to click File, Import. You need to import the .imp file that we exported from hypermesh. Click Model, and you use imp. Okay. I put my file here. No, okay, here. And now you click Open. You can see the model is here. Okay. Now you can put the boundary conditions and loading scenarios to run the model. Okay, I will show you step by step. Once we imported our model into Abaqus, we need to go to Mesh Part and let me put it here. Okay, and go to Sets. I'm going to isolate all the cartilage here. You see here. Now I'm going to change the element tab for these cartilages. Untick reduce the integration. Click OK. Okay. Now you can click interaction. Okay. So next step, we need to define. Okay, maybe I can explain it to you a little bit. So this will be our boundary conditions. So first, we need to establish a contact between cartilages. We are going to create 5 pairs of contact, and then you need to define boundary conditions for each piece of bones. And we are going to use 3 loading steps. So first, we will going to bring all pieces of bones back as you wrote them down here. Okay, and the second step, we are going to leave the talus free to rotate and move. The last step, we are going to apply a huge force of 2000 Newton on the tibia here. Okay, that's all the boundary conditions that you that you need to use. Okay, let's go back and do it one by one. So here, we need to establish contact between these cartilages. Before we establish contact, we need to create a surface. We need to create a surface for each cartilage. Okay, so let's do it one by one. Let's define tibia surface first. So I will call it tibia surface. Continue, and then you need to go to here, sets, and you need to find the tibia surface here. That's why you need to name each component uniquely, and it must be easy to recognize. Okay, so here we have our tibia, and okay, so select the surface. You can click, you can hit middle mouse button or just click down, and now you have one surface. You can click another surface, which is a fibula surface. Okay, so continue the same step. Go to here, choose the fibula cut here, and select this region. Okay, you have two. Okay, and the next one is the calcaneus. Okay, calcaneus surface. Continue, and then go to cal cut. Select all of them. The last one will be lavicula. Lavicut. After you have defined all cartilages, you can see here. You can hit all of them, highlight all of them, and see. Okay, it looks good. And now we are going to define surfaces on talus bone. In order to differentiate them, as I have mentioned, their contact comes with pairs. So you will have another calcaneus surface on talus bone. So this one we will call it. Okay, I like to do it one by one from the top. Tibia. Here we have one surface for both tibia and fibula cartilages on adjacent bones. In order to differentiate them, I will put TL here to represent all cartilages on talus bone. Okay, continue, and you click here. You select the tibia fibula cut TL. Okay, this is the tibia fibula cartilage on talus bone. Just click this one, select. Okay. Next one, I'm going to define calcaneus surface on talus bone. Same step, select calcaneus cut TL. Okay. Select. Here we have one small surface called lavis there. This limb is a bit long, so I would use it directly. Sometimes I call it calcaneous stair, sometimes I call it lavicular stair. It's the same. It's just this small piece of surface. So the last one is the lavicular surface on talus bone. So you select the lavicut, okay, and okay. Now you can see you need to switch it to any cartilage on adjacent bones, and then you can select all of them by, you can hold shift. Now you can see all the surfaces that you have defined will display here. Okay. This is a very good way to check if you miss any surfaces or not. You can also remember in total we have 8 surfaces. Okay. Now you can display all of them. Okay. Now I'm going to define contact for this model. So I'm going to create a contact interaction property. Here I only have one interaction property, so I'm going to use the default link. But if you want to change it, you can do it. First, I'm going to use penalty for fraction formulation and put 0.01. This is the fraction coefficient. And next, I'm going to add a normal behavior. Just add it and click OK. And then I'm going to define contact surface. Okay. Well, as I mentioned here, we have 8 surfaces. So it means we at least have we have 1, 2, 3, 4, 5. We have 5 contacts here. Okay. The first one will be tibia contact. It will be contact between tibia bone and talus bone. And you need to click a surface to surface contact, and you don't need a create surface. So here you need to select a master surface and a slave surface. So for this one, because both are soft material, so you can just select the area, the cartilage area, the bigger cartilage area as the slave surface. Okay, for this one I'm going to use tibia cartilage on tibia bone as master surface. So it's tibia, okay, it will be this one, and continue. And then I'm going to select the tibia fibula surface on talus bone as the slave surface. This tibia surface, this one. You can see the slave surface is in pink color and the master surface is in red color. So you need to tick exclude shell and cyclists. Here we don't need it. And click OK. Now you have defined one pair. So you can check one pair of contacts. You can check them here. You can see you created one pair of contacts. Okay, let's go to create. Let's create another contact. So we call it fibula contact. It's a still surface to surface contact. So here I'm going to choose this surface as the master surface and this surface as the slave surface. So fibula master surface and slave surface will be fibula, this one. Okay. Click OK. Yeah. Now we have finished the 2 pairs of contacts, and let's continue. creating contacts here. So the next one will be calcaneous contact. So I'm going to choose because here you can see we have a small cartilage surface on talus bone. So I will use the cartilage on talus bone as the master surface, and cartilage surface on calcaneous bone as sleeve surface. You can see here, we'll define it here, right? And they are, now we have two more, okay? So I'm going to call it Lavi stair contact. So we are going to choose this small piece of cartilage on talus bone as the master surface. So it's a Lavi stair, okay, on talus bone, and calcaneous surface on calcaneous bone. Lavi stair, okay. We can double check this later. I'll show you how to check them. The last one is the lavicular contact. So lavicular contact, we are going to use this one as a master surface. So it's lavi, and we are going to use lavicular cartilage on talus bone as the sleeve surface. Now you have defined all possible contacts in talus joint. So the model is heavy now because we have defined many things here. In order to check if you used all surfaces or not, you can visualize all of them here. And check them one by one. Here, so you click this one, double click. So you can see we have a contact between calcaneous cartilage, and we also have a contact between fibular bone and talus, and we have a contact between talus and lavicular, and here it's a little bit weird. Okay, yeah, now you can see. Okay, yeah, it looks all good. So I'm going to move on to the next step. So now we have created all contacts, and these contacts will be used in the entire simulation, no matter how many steps you have, okay? And the next step we need to create some rigid bones, and these bones will be used to apply boundary conditions. Before you create rigid bones, you need to create reference points first, because rigid bones have to be associated with a reference point. So you can click define one reference point for each bone. Okay, here let's rotate it a little bit. It's heavy. That's why it's a little bit slow. After you created a reference points, next part you can create a rigid bone. and you change the name. First one we call it tibia region. So you need to pick this reference point, and then you need to select the elements. We are going to select part of this part of this bone, but it's not easy, so we can just display this part. Now it's easier. Okay, so select a small layer of this one. Okay. Display all of them. Create a fibular rigid. Okay. Select this one. And here, if your fibula and the tibia is far from each other, you can just do it like this, and hit middle mouse button, or just click down, click OK. Now we are going to create talus rigid. Select this piece, this reference point, and select the body. Here you need to display only part of them. Set, you select tibia, no, you select talus, sorry, talus. I usually just select triangular elements because I don't want constrain solid elements. Okay, so select this part. You can see we select part of these elements. So we can click, sorry, we can just hold a Ctrl to unselect this. And then you can click down or hit the middle mouse button. Click OK. Display all. Now I'm going to create another rigid bone. Okay, yes. Select this. Select the reference point. Let's change the view. Not too much. Let's okay, zoom out a little bit and select this bottom. Let's create the last one, levy region, and we select the reference point. Select this part. We hit middle mouse button. Now we have successfully defined all rigid parts, and next part we need to define a constraint for these two pieces of bones. We need to create a set for T. You need to use node, and you need to choose a different point than this reference point. Okay, if you use the same one, you will get error. Okay. You can select any point except this reference point and this rigid point. If you successfully created a set, you can see here. Now I'm going to say create another set F. This time you need to use geometry. Use this one. And you need to define a constraint for these two pieces of bone. Use equation, because I want fibula and tibia move at the same time along that direction. So I call it a fib-tibia equation. So their relationship is defined using a equation. So I'm going to constrain this degree of freedom. 3 means z direction. Click OK. You can see once you have defined equation constraint for your model, you can see here you can have a single point. Yellow circle. Now we have defined all things that we need, and we are going to run this model using 3 steps. Okay, first step, as I show you on the first step, we are going to bring this piece using adjacent bones back. Second step, I'm going to unconstrain talus bone. The last one, I will apply a load. Okay. So the first step, we call it initial contact. So we need to click on and give this to 1000. It's the median. Initial 0.01. It's 8. Okay. Okay. Here I'm going to apply boundary conditions. Talus fixed. So in the first step, we are going to fix talus. And the tibia display. we are going to give a displacement for this piece of ball. So how much geometry? Select this reference point and hit middlemost button. Select all of them, and then you need to check for tibia. We need this displacement to move it back. So you put lective 2.5 and lective 3. Negative 2.5 for x, negative 3 for that direction. You can see here the displacement will show up here. It shows this piece of bone will move along the direction of these two arrows. Next, we are going to define boundary conditions for fibula. Here, you don't need to select 3 because we already constrained fibula have the same displacement in that direction with tibia bone, so you don't need to select this one. Click OK. No, before you click OK, you need to check for fibula. You can see we defined the same distance along that direction, right? So it means they are going to move together, and we are going to put 1.5 for x direction. 1.5. Click OK. You can see fibula will move along this direction. And now we are going to define calcaneus displacement, and for this piece of bone geometry, you need to select all of them and check how much displacement we have here. So it's 2 in y direction and 3.5 in z direction. 2, 3.5. Click OK. The last one, lavicular displacement. Geometry, this one. Check lavicular, we have lective 1, positive 4.5. Lective 1 and 0.5. Lective 1.5. Okay, click off. Now you have successfully defined the initial contact step, and then we are going to create another step called adjust. In this step, talus bone will change its position freely. Remember, for this step, it's better to use the unsymmetric for metric storage. Click OK, and you click boundary conditions in second step, and just deactivate talus fixed. Okay, that's it. Now in the second step, the other boundary conditions will be fixed, and you can move a tip and talus freely. This step, the last step, we are going to apply a load. .01. It's 8. Use unsymmetric. Click OK. And here, you need to deactivate tibia displacement and fabula displacement. And we are going to define another two, a new tibia displacement. Here, because we are going to apply load here, so you don't want to apply any displacement here anymore. So here we just put it negative 2.5, and that's it. And for new fabula displacement, click geometry, this one. Last time we didn't select this one, right? This time you needed to unselect U3 and UR3. Okay. And give this one 1.5. Here, 1.5. Here. And last thing we need to do is to apply a load on this point. So the direction will be 2000 Newton along Z direction, negative Z direction. So you put a negative 2000 Newton. You can see this yellow arrow shows the direction of your load. Now you have defined all boundary conditions. You need to create a new job. I will define it as PI and bio and hit continue, click OK. You have a model here. Now you need to submit your job. You can also open monitor. If there is anything wrong, you can check. You can see it from this window directly. This model is a little bit heavy because we have many elements. So it might take 8 to 10 hours to finish the simulation. Yeah, so you can submit your job and check your simulation later. So if you see this message, I don't know, analysis input file processed and completed successful. It means your model, there is nothing wrong with the definition of boundary conditions, material properties. All these are good. If you can't see this step, it means there is something wrong with your boundary conditions, material properties, or other things. The model can't even run its very first step. Okay? So I will show you how it will look like if the model is running normally. And after that, I will kill this model because it takes a longer time. And maybe in the next video, I will show you how to run this model without using this GUI interface. Okay. You can see there are some warnings here, say that these elements are distorted. It's okay because our geometry is highly curved. You will have this message anyways, but make sure it's not too much and it's not critical. if they are if they exceed a certain number of elements, your model will be difficult to run. Okay. You can also check here. Message. A message shows if your model is running or not. Yeah. If you have finished any step here, if you have finished any step, you will see them here. So the first step, the increment, you can see here. The first step, the increment is 0.01. It's very small. Okay. And if you see these numbers and you see it's not 0, it's 0.01, it means your model works fine. And yeah. So I'm going to kill this model, and in the next video I will show you how to run this model after I will show you how to run this model without opening this GUI, because it will be faster. Okay. Kill. You can see it's terminated, and you can find this file. You can find your file here under this task. Okay. So I like to save this model because sometimes you might need to modify it if there is anything wrong later. Okay, so you can keep it for a while. Just click OK, and that's it for today. Thank you.